Hello, my friends. Thank you very much for subscribing to our channel. Some questions are designed to train our observation abilities. And sometimes observation is more efficient than calculation. For example, our today's question. There are 10 islands in a lake, which are connected by 15 bridges. Question. In order to completely disconnect Island A and Island B, at least how many bridges should be closed? Why not give a try, and we will come back soon. This question can be easily solved through observation. However, if we really want to calculate it, then it's not that easy. The most straightforward, and probably also the least efficient algorithm, is something like this. Among those 15 bridges, everyone has the choice of being closed, or not being closed. Therefore, there are a total of 2 to the 15th power possibilities to close parts of the bridges. Among them, one can find those solutions, where A and B are not connected, and then select the one with the least number of closed bridges, and that is the correct answer. Of course, in practice, no one will really adopt this whole algorithm. Since the question is about at least how many bridges should be closed, we might as well start with the possibilities of closing only one bridge. If there is already a case for A and B to be unconnected, the calculation is over. If not, go ahead and discuss all the possibilities of closing 2 bridges, and so on. Generally speaking, as long as the number of bridges is not too large, the calculation will be much smaller than 2 to the 15th power. If the number of bridges is really large, other algorithms can also be adopted. For example, the following one. We can first close all the bridges which connect Island A to the outside, 1, 2, 3, 4. A total of 4. In this case, Island A and Island B are naturally disconnected. What if those bridges connecting Island A are not closed? We can regard one or several small islands, which are connected to Island A, and together with Island A, as a whole. Like this. And then close all the bridges which connect them to the outside. 1, 2, 3, 4. Still 4. After closing them, A and B are of course also disconnected. For another example, these 4 islands are regarded as a whole. 1, 2, 3, 4, 5, 6. And 6 bridges need to be closed to completely disconnect A and B. Because there are 8 islands except for Island A and Island B, so the theoretical upper limit of this algorithm is to calculate 2 to the 8th power times. But because in some cases, the selected islands cannot be connected with Island A by themselves, the actual calculations are generally fewer than 2 to the 8th power, or even much fewer. Moreover, for any case, A and B have been guaranteed to be completely disconnected, so there is no need to additionally check the connection between A and B, so the calculation load will really be smaller. But in fact, this is an exercise at the 6th grade level. For the students in this level, it is already easy to find the answer only by observation. The second algorithm mentioned above will somehow play some supportive role in this observation process. For example, we regard these 3 islands as a whole, or regard these 4 islands as a whole. They can be connected to the outside through these 3 bridges. Closing these 3 bridges can therefore completely disconnect A and B. Except for that, there is no other solutions with fewer closed bridges, and the answer to this question is actually 3. Thank you for watching, and see you next time.